Welcome to Chapter 5, Chirality. This is going to be a lot of questions, a lot of work. You're going to have to practice them, and the more practice makes perfect. Okay, for this problem you need to draw three-dimensional structures. The goal here is to see if you can draw mirror images. For some compounds, it is the only way to really determine whether you have an enantiomer or if you have an achiral or an achiral carbon. Okay, so the first one is cis 1,2-dimethyl cyclobutane. If you were to draw the mirror image, you would draw it like this, with the methyls on the same side going down. Now, this has a plane of symmetry, so if you see that your plane of symmetry is this way, then these are identical. So anytime you find a plane of symmetry, that would be achiral. It means they're the same molecule. Now the next one is trans. And so if you draw your trans mirror image, you'd make one methyl going down, and then you'd make one methyl going up. And then if you draw your mirror image, you draw this methyl going down, this methyl going up, and then what you want to do so this is compound number 1, and for compound number 2 you want to rotate 180 degrees your mirror image that you drew. And so what's in front, so this is in front, will go back. So this is front, and what's in front will go back. So then when you redraw this, you'll see that the methyl going down is down, and this methyl going up is up. So now those are in back. And then what you do is you superimpose, this is called number 2, you compare these two, and you ask if they're superimposable. So if you can see, this methyl is in front, this methyl's in front, and if you were to overlay these here and these are in back, you would see that they're different and they're non-superimposable. So that's that word, and it's superimposable, and that makes them chiral. That means they do have mirror images that are non-superimposable, and this makes them enantiomers. Okay, the next one we have cis and trans. So let's do cis first. Now the connectivity is different here. This is on 1, 3. So here's the 1 and the 3. Draw the mirror image. Let that go down. And then this is here, and this would go down like this. And these also have a plane of symmetry. You can see that way. So these are achiral. They're identical. Okay, now if you do the trans, so to draw the trans here, we draw the mirror image. So this one has the CH3 going down, says the CH3 going up, and these are also identical. So those are achiral. The next one is 2-bromobutane. So draw out 2-bromobutane. 1, 2, 3, 4. 2. And you need to draw this with a stereo center to really see it. You can draw the mirror image if you want. I think it's good practice. to draw mirror images, and then you would rotate this mirror image, and when you rotate it, so this is on one side and now it's on the other side. So let's make sure I draw this. Not what I wanted. Okay. Okay, so this is coming down. Okay, that's coming down. This is going up. And let's just start all over. Okay, so this is coming down, up, down. And so this is on this side now. So this ethyl's on this side. And what was once coming at you, so now the hydrogen's coming at you. So this would be the hydrogen, and the bromine would be going back. And then you would compare these two. The rotated 180-degree mirror images and number 1. Also, you can just look at this and say, okay, this is an asymmetric center. We got bromine, we got ethyl, we got methyl, we got hydrogen. So if you didn't want to fool with the mirror image and stuff, you could just say we have one asymmetric center, so this is definitely a chiral molecule. Now for these molecules here, you really do need to draw the mirror images. So this is the mirror image, and then you rotate it 180 degrees. We're going to compare this first original one. Now, so as you can see, this ketone is in back. Okay, so when we rotate this 180, not only is it in back and on the left-hand side, it's going to be in the front, and it's going to be on the right-hand side. Okay, so when we rotate this and redraw it, now this ketone is in front, and this is compound number 2. You want to compare these two, and if you lay one on top of the other, you see that the original ketone is in back, this one's in front, so those would be non-superimposable. That means it's chiral, and they are enantiomers. Okay? This compound here, you don't have to draw the stereocenter. There's no stereocenter because this is an OH. We're looking at this is a methyl, and then CH2, 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 they meet. If you take your finger and you go all the way around the ring, and you do not have any point of differentiality, and you come and meet yourself, okay, so then you have an achiral compound because you do not have a stereocenter. Okay, for each compound, determine whether the molecule has an internal plane of symmetry. Okay, so methane does. The best way to do this is we're just going to, since we have so many problems, and methane, you don't have an asymmetric carbon. Okay, so we're not even going to bother drawing that. You can say that has a plane of symmetry. The cis, typical cis compounds typically do. So this has an internal plane of symmetry. So this is achiral. Methane's achiral. Trans, 1,2 bromo. I keep choosing the wrong thing here. Okay. We'll redraw this here. Trans, 1,2 dibromo butane, and that has no plane of symmetry, so the trans, so that means it's chiral. Okay, so this one's chiral. We'll put the chiral in red. 1,2 dichloropropane. Dichloropropane would be, okay, not the cyclo, so 1,2 dichloropropane. So let's look at this. Let's look for an asymmetric carbon. This carbon here is bonded to 2 hydrogens, so it's not asymmetric. This carbon here, though, is bonded to a chlorine, a methylchlorine, a methyl, and a hydrogen. So this would have an asymmetric carbon, and therefore this would be chiral. This would be a chiral compound. Glyceraldehyde. Glyceraldehyde, just look at the carbon there. This is an aldehyde, which is like this, CHO. If you do your Lewis structures, this is an OH, this is a hydrogen, and this is a methyl alcohol. So this would definitely be chiral. It has an asymmetric carbon. Carbon's connected to 4 different things. Okay, this compound here has a plane of symmetry. And if you couldn't see that, you could, so if you thought that this was the methyl was your asymmetric carbon area here, then you could go with your fingers and you would reach each other on the ring. So if you went this way and vice versa, you would come to the same point, and that means it has symmetry, and that means it is achiral. This is your amino acid alanine, and so this carbon here, the central carbon, has a carboxylic acid, a amine group, a methyl, and a hydrogen, and that makes it chiral. It has an asymmetric carbon. This compound here, the bicyclos, remember I told you these are good to draw your mirror image, and then you want to rotate them 180 degrees, and then what is on one side will now be on the other side, and what is in back will come in front. And then if you compare these 2 compounds here and you try to superimpose them, you would find that this is superimposable, and that makes it achiral. Okay, so more of this. You want to assign R and S this time. So this should be 1 bromo, 2 methyl butane. So let's go ahead and draw that out in our line structure. 1 bromo, 2 methyl. Now the best thing for you to do then is to look for an asymmetric carbon. Now the first carbon off the bromo is a methylene, which is a CH2, methylene. So that's not going to be asymmetric. This is your only asymmetric carbon here, and that carbon is connected to a methyl. So it's connected to a methyl, it's connected to an ethyl, it's connected to a CH2 bromo, and a hydrogen. So now you want to rank your priorities. So obviously you do this by atomic number or molecular weight. So atomic number for hydrogen is 1. I do weight usually. So the carbon bromine bond here is like 12 plus 79. This one's a carbon carbon, so that'd be 12 plus 12, and then this is just 12. So obviously the highest priority will be this one here, number 1, and then number 2 will be this one here, and then number 3 would be your CH3. Now we have to draw this, let's pick one coming at you. You have to draw this, your asymmetric carbon, with a wedge and dash, and in order to assign R and S. So here we have connect 1, 2, 3. When you connect those, you'll see that that's counterclockwise, which makes it S. Okay, and hydrogen's not shown here, but it would be in back, so we can keep this as S. And if you were to draw the R then, so the R would just be, you could just draw this methyl group coming at you. Okay, the next compound, Chloro Cyclohexane. So just pick one, Chloro Cyclohexane, and then we can see that we do not have an asymmetric carbon. You can tell this because you got chlorine, you got hydrogen going back, but then you just, this is a methylene, and then you go to the next methylene, and then you see that you meet yourself, okay? So this is achiral, this is achiral, and it has no asymmetric center, no asymmetric carbon. Okay, 2-pentanol, do you see that this carbon here that's starred, make it red, is your asymmetric carbon? And so then to do this one, you want to draw, just pick one like the OH coming at you, hydrogen going back. You assign your priorities. Okay, so what do you have? You have the OH, talking about what's coming off of this carbon here. We have CH2, CH2, CH3. We have a CH3 and we have a hydrogen. So hydrogen is going to be 4, the lowest priority. Oxygen is going to be 1. And then you have propyl, which is going to be 2, because the carbon then goes to another carbon. And then this carbon will be 3. So then we have 1, 2, 3, 4. And then you connect the dots, and you see that that's clockwise. Clockwise is R. The lowest priority is in back, so R stays R. So this one's R. And then if you were to draw S, you would just draw the OH going back like this, and that would be your S, enantiomer. 3-pentanol, as you can see, you do not have an asymmetric carbon because this is an ethyl group and this is an ethyl group. So this is achiral. And then you can go on. Alanine, we've seen alanine before. We have to draw this here. So let's draw, you just put the amine coming at you. Make sure you put your dashes and wedges on the same side. CO2, H, and CH3. Now if you want to assign your priorities, hydrogen's 1, so it's in back. Nitrogen versus carbon. Nitrogen has a higher atomic number, so that would be 1. And then we have a carbon and a carbon, but that carbon's connected to 3 hydrogens. This one's connected to 2 oxygens, so this would be 2. And then that would make that 3. So 1, 2, 3, 4. That would be R. And so then if you wanted to draw your S enantiomer, you would just draw the amine coming, going back. Okay, let's look at G. Okay, so let's look for asymmetric carbon here. This carbon cannot be asymmetric. Do you see that's sp2? Okay, so the asymmetric carbon would be this one. So let's assign your your numbers here. So you have, we'll write them out here. You have a CH2 and a CH2. That's a CH2 and a CH2. And you have a hydrogen, and then you have a C bonded to another C, bonded to another C, bonded to another carbon. So that red carbon here is bonded to 1, 2, 3 carbons. 1, 2, 3 carbons. So that's obviously going to be number 1. Hydrogen is going to be number 4. So make this 1, make this 4, and then you don't know yet for your other CH2. So then you go to the next one. This is a CH2, and this is a carbon bonded to another carbon, bonded to another carbon, bonded to another carbon. So this would actually be number 2. Okay, so this whole side. So then this would be 3 over here. And then you would connect 1, 2, 3, 4, and that is clockwise. That's R. Hydrogen is in back, so it would stay as R. And then if you wanted to redraw this as the S enantiomer, you would see how you have hydrogen in back. Now you could draw in back hydrogen in front, and then you could draw it let's do it this way just to make sure. Hydrogen, CH3, HH. Now, do you have Cysts and Trans isomerization? Because you have that double bond, and the answer is no, because on one of those carbons, you have the same thing. They both have hydrogens, so you don't have to worry about cis and trans. Okay, this molecule, once again, on H, you need to draw the mirror image, and then you're going to need to rotate that molecule to draw the enantiomer. So this is the enantiomer. That's its mirror image, so that would be one and that would be the other. You can rotate that 180 degrees. What is in back, this is in back, this is in back, will now be in front. And what is on this side of the molecule is now on that side. And then when you compare those two, you can see that these are not superimposable, and so therefore those are the chiral, and that's the enantiomer. For I, let's see. Let's just draw once again, with the rings, it's best to draw your mirror image. So let's see if I can get some space here. Draw my mirror image. So I'm going to draw the 5-membered ring here. Hydrogen there, and this is here. Now, this is our number 1 structure. We're going to rotate this 180 degrees. Now, when I rotate this portion of the molecule is going to be on the other side. I'm going to draw the 5-membered ring here. And keep our hydrogens going up. And our double bond is here, it's in front. It's going to have to go in back. So what is on the right-hand side now is on the left-hand side, and what is in front must go in back. And then that gives us compound number 2. So we're going to compare these images, and if you were to lay compound number 2 on top of number 1, you would see that this double bond here would be in the front, where this would be in the back. So it would be non-superimposable, and these would be chiral, and this would be the enantiomer of the original compound, because it's this mirror image, this non-superimposable. Okay, number 4, we are going to find each asymmetric carbon, that means a carbon connected to 4 different things, and determine whether it has R or S. And we will have to star it. So the asymmetric carbon, I'll show you, is here. And then we need to assign our priorities. We have hydrogen is 1, or the oxygen, the alcohol. Then we have a CH3 and an ethyl. This is going to be 2. And then methyl is 3. Hydrogen is 4. We connect the 1, 2, 3, like the dots. That is counterclockwise. Counterclockwise is S, but is our hydrogen in front or back? It's coming at us. So we're going to have to switch S to R. So this is R. Okay, so A is R. Let's do the next one. Okay, do you see your carbon that's connected to 4 different groups? Yes. So we can give hydrogen. We can go ahead and assign that 4. Now we have bromine. Bromine has a molecular mass of like 79, so we're going to make that 1. Now we have this CH2 or CH3. So this one's going to be 2, and then the ethyl is going to be 3. And then we connect the dots, 1, 2, 3, connect those numbers. Just ignore 4, 1, 2, 3. Now what is that? Is that clockwise or counterclockwise? Yes, that's clockwise, so that's going to be R. But our hydrogen is in the plane. Do you see how it's got a straight line? It's not in the back, so then R has to be switched to S. And so that compound would be S. Let's go to the next compound. And see, just because it's drawn this way doesn't mean, with dashes and wedges, doesn't mean that it's asymmetric. So look at this. We have a methyl, and we have a methyl group here. Okay, both those methyls are the same thing. So the only asymmetric carbon you have is this one right here, because that carbon has a CH3, a hydrogen, a carbon double bond, and a carbon with CH3 and CH3. Okay, so those are the four groups on that asymmetric carbon. Now if we're going to give them priority assignments, hydrogen would be 4. This carbon here is connected to 2 carbons. This one's connected to 2 carbons. So now we'd have to say, okay, well then you look at the next carbon here, and this carbon then you would have to say is connected to 2 carbons. This carbon is just connected to the 1 carbon. This carbon is connected to the 1 carbon. This carbon is AA bonded, so it's connected to the 2 carbons. So this would have to be number 1 priority. The other would be number 2, and then the methyl would be number 3. So when you find this would be 1. And we said this would be number 2. This would be number 3, and this would be number 4. Now you want to just ignore 4 and connect 1, 2, 3. And you see that you are going clockwise. So that's R. And then is hydrogen in back? Yes. So R stays R. Okay. The next problem is a trans 1,2 dichloro cyclopentane. And there's no symmetry there, so it would be, is it asymmetric? Yes. So let's just see what we have to do rings. We have 1, so we're doing this carbon here. We have 2, assigning priorities, 3, and 4. So 1, 2, 3, so that would be R. And I guess you'd have to draw this as chlorine coming up. So if chlorine's coming up, then you'd have to put that in the back, and this chlorine would be going down. So this one's kind of tough. Let's see. Okay. Okay, to sign R and S. For this one, let's redraw it. Okay. And like I said, we're going to have to assign one of these coming at you and one of these going back. So when we do this, hydrogen is 4, chlorine is 1, and then this would be 2, and this would be 3. So 1, 2, 3 is R. And then you come here to this carbon here, chlorine would be 1, this whole group would be 2, and this back group would be 3, 1, 2, 3. That's R. However, hydrogen now is coming at you, so this would be S. Okay, for the next one, we have chlorine both on the same side of the ring. So let's put chlorine going down and hydrogen going up, just because that's what it looks like. And let's assign these 1 and 2 and 3. 1, 2, 3. So we call that counter. Counter is S. The S has to go to R because of your hydrogen, so this one's R. And then you come over here. This chlorine's 1. This one group's 2. This group's 3. Connect the dots. That's R because it's clockwise, so it's R. But your hydrogen is coming at you, so R goes to S. So this one's R and S. Okay, so the next one here, your asymmetric, let's just go ahead and These are your asymmetric carbons. You're supposed to star them. Okay, so your asymmetric carbons then for this one would be this hydrogen here coming at you. This one would be going back because it's in back of this. And so your groups then of assigning, this would get number 1 because it's a carbon double bonded. So that carbon is bonded to 2 carbons. This carbon is 1 carbon, that's a methylene. So then this would be number 2 because when you come down here, you see that carbon is bonded to 2 other carbons, and this bond is only bonded to 1. So 1, 2, put a 3 there, and then connect 1, 2, 3, and that's counterclockwise. So that would be S, but the hydrogen's coming at you, so then we call that R. So the first one here is R. The back one, this would be 1 with a carbon-carbon double bond, and then 2 still at the top here, this bridgehead, and then 3. So 1, 2, 3, that's counterclockwise, and that would be S, and the hydrogen still staying in the back, so that would stay S. So the front one is R, and the back one is S. Okay, the next one. Okay, let's find our asymmetric carbon, and it would still be these hydrogens, these bridgehead hydrogens. This one's going back, this one's coming at you. So for your assignment, this would be 1 because it's carbon double bonded, so that's carbon bonded to 3 carbons. Then your next one would actually be here because you go from CH2, CH2, and then this one, let's look at that one. That one's bonded to a C, C, C. So 2 carbons. And when you go here, this is bonded to 2 oxygens because it double bonds 2 oxygens. So we would call this 2 and then that 3. And then when you connect 1, 2, 3, you see that that's counterclockwise, that's S, but you have your hydrogen coming at you, so S would go to R. So that front carbon, asymmetric carbon, is R. Now for the back, you have carbon double bonded to oxygens, so that would be your highest priority, 1. Then your carbon double bond would be 2, and then your bridgehead would be 3. So 1, 2, 3 is clockwise, and clockwise is R, and you get to stay R. So G is RR. Your asymmetric carbon here would be this carbon here with the methyl group coming at you. You assign your priorities. What you don't see then is hydrogen in back. You have 1 for the carbonyl because that's carbon bonded to 2 oxygens. Then you have the CH2 because that carbon is bonded to another carbon. And then you have your CH3. So now you do 1, 2, 3, and you see that's clockwise. So that's R, and R stays R because hydrogen's in back. This last one here, your asymmetric carbon, would be this carbon here. As you can see, this carbon is bonded to methoxys, which are the same. This carbon is bonded to methyls. This one's an sp2 carbon. So this is your only asymmetric carbon. Now let's look at what we have here. We have a carbon double bonded to oxygens. We have a carbon that's double bonded to 2 carbons. Then we have this carbon that's bonded to 2 carbons. And then we have this carbon which is bonded to 2 oxygens. So we have a tie between the carbonyl and this O-methoxy group. So then you have to look at, well, this oxygen is bonded to a carbon and another carbon. This oxygen is bonded to only 1 carbon. So the highest priority would be a 1 here, and then this would be 2. And then between these two, the double bond would win because then you go out to the next carbon, which would be this carbon, made it in blue, and this carbon is bonded to a CH3, And this carbon would technically be bonded to another carbon because it's doubly bonded back. So this would make this a higher priority, and that would make that 3, and that would make that 4. So in this case, your lowest priority is not a hydrogen. So go ahead and just ignore the 4 and connect 1, 2, 3. That is counterclockwise, so that's going to be S. And then, but you see that your lowest priority is coming at you with that wedge, so then we have to switch S to R. So this compound, the configuration is actually R. Okay, so this is assignment 5.2, and we're going to be talking about polymetry. This is some math. You're going to need a calculator, and this is how to calculate your specific rotation. Specific rotation is usually noted like this with the alpha, and then the sodium D line is D, and it's at 25 degrees because it's temperature sensitive. And this is basically the formula. It's the observed rotation over your concentration times your length of your cell. And so the units, of course, for this actually is unitless. So you just make sure you use these units and you don't have to worry about canceling them out. So this is going to be in degrees at the top, your alpha. And then your concentration needs to be grams per milliliter, and your length of your cell needs to be decimeters. So if you get in centimeters, you need to convert it out. So obviously, concentration is mass over volume. So you just do C equals 2.0 grams divided by 10.0 milliliters, and that's going to equal 0.20 grams per mil. And then you place it in a 100 millimeter cell. Okay, so then we got to convert that to decimeters. So 1,000 millimeters into 1 meter. 1 meter, you have 10 decimeters. So then you cancel out your zeros, 1, 1. 100 divided by 100 is 1 decimeters. So now you can just go, make sure this is positive. That means it rotates light, a single plane of light. It rotates that light, this enantiomer, by a positive, a clockwise, not counterclockwise, clockwise, 1.74 degrees, and then we do 0.20 times 1 decimeters, and you know what, you don't even put the units in, and that works out to be positive 8.7 degrees for plus glyceraldehyde. And that is your specific rotation. Okay, so let's do this again. You have 0.50 grams of epinephrine, and it's dissolved in 10.0 milliliters. So it's asking for the specific rotation, so let's apply your formula. It's 25 degrees Celsius using sodium D line, so you just do this. You're going to do your observed times your concentration times your length of your cell. And so it tells you the observed is negative 5.1 degrees, and your concentration then would be 0.5 grams divided by 10 milliliters, which end up being 0.050, and then 20 centimeters for your length. Well, you have to convert that to decimeters, so 100 centimeters, 1 meter. For 1 meter, you have 10 decimeters, so cancel out your zeros. 20 divided by 10 is 2, and so you just put these in without units, 0.05 times 2, and that gives you a negative 51 degrees, and it's negative, so you'd say 4 negative epinephrine. This one is telling you, gives you a product that's slightly okay, now you're given the specific rotation. So it's telling you the specific rotation is a positive 45 degrees and wants you to calculate the percentage of the positive 2-butanol and the negative 2-butanol. What you need to know in this problem that's not given to you is you need to know the rotation of the pure positive butanol. Okay, so that's a positive 13.5 degrees. So then you're going to do observed rotation divided by your rotation of your pure enantiomer. So then you'll do positive 0.45 degrees over a positive 13.5 degrees, and you'll multiply that times 100%, and that's going to give you 3.3% optical purity. Okay, that gives you the purity. That means it's 3.3% enantiomerically enriched. This is excess of, and it's a positive, see, positive 0.45 of the positive enantiomer, because you get the positive and the negative. So then what I do then is I just add this onto 100%. So 100% plus the enantiomeric enrichment is 103.3%. Then you divide this by 2. So 103.3% equals 2 times, because more than half is this, belongs to the positive, 2 times the positive enantiomer. So you solve for the positive enantiomer by dividing by 2, and then that's going to be about 51.6. You might have gotten 51.7%, depending on how you round. That's your positive enantiomer. And then so your negative enantiomer is going to be 100% minus your 51.6%, and that's going to give you 48.4%, and that's your negative. Note that the positive and negative need to add up to 100%. So basically, when you do these ratios over the known, the pure enantiomer, you're getting the excess, the 3.3%. You have to add that up to 100%. Then you want to divide that by 2. And since it's positive here, you know that's your positive. And that number's got to be greater because that's excess. Okay, the next problem. Positive tartaric acid has a specific rotation of 12 degrees, positive. Calculate the specific rotation of a mixture of 68% and 32%. Okay, so if you have 68% of your positive and you have 32% of your negative, well, 68% will cancel out 32%. So we need to subtract these. So 68% minus your 32% equals 36%. This will be your excess. So you always kind of want to find your excess, and this is your positive. So it's going to be positive excess. And then if you're given, so the specific rotation of 12 plus 12 degrees belongs to your excess. So then you can just multiply this by essentially 0.36, your percentage, and you'll see that plus 4.3 degrees is the specific rotation of the mixture. The specific rotation of S enantiomer is positive 15.9 degrees. Draw the structure of the S iodobutane. Okay, so let's go ahead and draw the structure. That's 4 carbons, and on 2 you have iodide. Now, what's on carbon number 2? Now, iodide will be 1 priority. This will be 2, and this will be 3. So 1, 2, 3. That would be R if we have it coming at you. So I'm going to make a little dashes coming back, and I'll make hydrogen coming at me. So let's just check this again. 1, 2, 3 is clockwise, which is R, but the hydrogen's coming at me, so I'm going to switch this to an S, and it wanted S. So we're good there. And it says predict the rotation of R. Okay, so determine the percentage of R and S with a specific rotation of negative 7.95. Okay, so well, if the rotation of S is plus 15.9 degrees, okay, then the R would have to be equal in magnitude but opposite in direction. So that would be a negative 15.9 degrees for the R to iodobutane. Now I want to determine the percentage of composition with a specific rotation of negative 7.95. So remember, you put the observed over the pure. So here we have negative 7.95 degrees over the pure, negative 15.9 degrees. And then you want to times that by 100% because we want to find the enantiomeric enrichment. So when you do that, you will see that you get 50% EE. So then 50% EE is 2 times your negative component. So you divide by 2, and then so this will be 50% divided by 2 would be 25%. So since that's your enantiomeric excess, that means 50% plus 25%, which is 75%, must belong to the R enantiomer. That's the negative, okay, with a negative. And then 100% minus the 75% then gives you 25%, and that 25% would be the S enantiomer. And that's why it's negative, so it would be more. You can actually compare them. A negative 8 degrees compared to the pure is negative 16, and you could say, does that make sense? For this compound, you're wanting to indicate the relationship of each of the structures to the first structure. So this is your first structure. You have the same enantiomer structural. What I like to do here is I like to see it, I like to prioritize R and S, and then I can figure it out. Because if something is R, then an enantiomer would be S. If something's R and then the other compounds are, that would be the same. So let's look at this. So we see our asymmetric carbon here. These are called Fischer projections. And Fischer projections mean that what's on the horizontal are like bow ties and they're coming at you. So when you assign your priorities, which here you would make the oxygen 1, the carboxylic acid 2, the methyl 3, and then hydrogen 4. Now look at the Fischer projection. See, the carbon is always on the vertical line. And your most oxidized carbon, that means a carbon with more oxygens, it's always going to be your very top carbon. Now what you do is you connect the 1, 2, 3, and you see that that's counterclockwise. And we know counterclockwise is S. But since hydrogen is on a bow tie coming at you, then you're always going to have to switch these pretty much. So this is an R. So you know that your asymmetric carbon is R. Now, this is a structure, and this one's easy to see because you're going to have it set up the same, and you have your OH. This is a mirror image, okay? And when you make a mirror image of and you rotate the mirror image of a Fischer projection, what's on top goes on bottom, and what is left becomes right, or what is right becomes left. But you can go ahead and sign them, and you'll see that this will be an enantiomer, and therefore it will be an S. So let's just go ahead and do that. Oxygen is 1, carboxylic acid is 2, the methyl is 3. And like I said, this is a bow tie. So the hydrogen's coming at you. You connect the 1, 2, 3. That is clockwise. So we know that's R, but the hydrogen's coming at you. So we have to switch that to an S. So you can see that that's S, and it's an enantiomer. Now this one's harder to see because we don't have the carboxylic acid on the top, and we just have it a little different. So we're going to need to do our assignments. So this is your asymmetric carbon. Oxygen is 1, carboxylic acid is 2, the methyl is 3, hydrogen is 4, and what is on the horizontal, it's like a bow tie, it's coming at you. So now when you do the 1, 2, 3, you see that's counterclockwise is S, and this should be an H. This is a misprint, it should just be OH. Anyway, so that's counterclockwise, and it actually should be a CH3. Okay, that's okay. Sorry. So like I said, this is counterclockwise. Your hydrogen is going back now because the vertical is going back, so S stays S. So since your original compound is R and this is S, yes, these are enantiomers. This compound here, 1, 2, 3, 1, 2, 3, counterclockwise. Counterclockwise is S, but your hydrogen is coming at you, so S goes to R, and R, the first one's R, so this would be the same. So we have enantiomer, same. Okay, let's look at this next compound. Let's make sure it has an asymmetric carbon, and it does. It's this one here that's usually on the vertical, but you always want to see and check. Bromine is going to be 1, the ethyl is going to be 2, the methyl will be 3, and then hydrogen will be 4. And then you connect the 1, 2, 3, which is counterclockwise, which is an S. And the hydrogen is on the bow tie coming at you, so S becomes R. So this original compound is an R. So then when we look at this one here, this one is bromine's 1, ethyl's 2, methyl's 3, 1, 2, 3. This is counterclockwise, so that's S, and the hydrogen is coming at you, so S goes to R. So these are the same. So the first one is the same. Here we have R, bromine's 1, ethyl's 2, methyl's 3. That's clockwise, that's R, but your hydrogen's coming at you, so R goes to S, and S is the opposite of R, and so that is an enantiomer. Okay, the last one, 1, 2, 3, that is R, but the hydrogen's coming at you, so it's going to switch to an S. So this is S. S is an enantiomer. Okay, the next one are butanol. So let's see what we can draw here. 1, 2, 3, 4, and then you can draw your 2. Put an OH there. And then we go 1, 2, 3. That is R because it's clockwise. So we want to go ahead and make that coming at you. Okay. And then, so that one's R, and then you can just do this one. 1, 2, 3. Connect them. That's clockwise. That's R. The hydrogen's coming at you, so that's got to go to S. So the first one will be an enantiomer. The next one we have OH1, ethyl 2, 3, 1, 2, 3. That's counterclockwise, but your hydrogen's on the horizontal, so the S will have to go to an R. R is the same. Okay, here we have 1 OH, 2, 3. Connect the 1, 2, 3. That is counterclockwise. That's an S. Your hydrogen is on the horizontal, so you're going to have to switch the S to an R, and this would be R, and R is the same. Okay, so for this one, the Fischer projections, let's see, draw mirror planes. Okay, so you're basically seeing if you have an enantiomer, same structure, or an enantiomer. So you're looking for asymmetric carbons here. So this is, so So let's draw our mirror image. So we have an OH on this side and a hydrogen there. And you can see that these are different. There's not a plane of symmetry. So if you were to assign R and S here, if you wanted to, you could assign that. It would be 1, 2, 3, 1, 2, 3, counterclockwise. So S, but your hydrogen's here, so that goes to R. So this compound is an R. Here would be 1, 2, 3. That would be R, except your hydrogen's coming at you, so this would be S. This is S. These are enantiomers. Okay, because the OH is on the other side here, this is what makes Fischer projections nice. You can see, and you only have one stereocenter, which is the one horizontal cross. In true Fischer projections, every horizontal is an asymmetric carbon, and because the OH is on different sides and everything on the vertical are the same, then you should be able to just look and say, okay, they're enantiomers. One's R and the other one's S. So let's look at B if you want to do this quickly. Okay, so when you draw your mirror image here, you're going to see that just because it's drawn Fischer projection, this is the same. So this would be achiral. Okay, so these are the same structure. Here, you don't even have to draw it either because that carbon has 2 bromines. So this is going to be the same. It's going to be achiral. This one, when you draw the mirror image, you have 2 stereocenters. And so this would be an enantiomer because these 2 stereocenters would be the opposite. And you can sign them. This would be 1. CHO, that's 2, 3. So 1, 2, 3 is that S, and that would be R. So the first one's R, and then you go to the next one. That's 1. This would be 2, 3, 1, 2, 3, counterclockwise because the hydrogen's coming at you. It would be R as well. And then these should be SS. If it's a true enantiomer with 2 stereocenters, if you have one compound that's RR, then enantiomers would have to be exactly the opposite, SS. So let's just see, 1, 2, 3. That's R, but then R, because their hydrogen is coming at you, that would be S. Here we have 1, 2, 3, and that would be S as well. So yes, those are enantiomers. Okay, when you look at this one, you see that these 2 are the same, and this is going to be the same structure. It has symmetry, plane of symmetry. This one here, these are opposite, so when you draw it here, OH, you have OHs kind of like trans to each other. So you want to go ahead and draw that. And the best way to do this is to assign R and S. So there's 1. This would be CO. The C would be CO. That would be CO. And this would be CC. So this would be 2. This would be 3. So that's counterclockwise, which would be S, but your hydrogen's on the horizontal. So you have to switch it. So this would be R. And then this carbon here would be 1. This would be 2 and 3. 1, 2, 3. Counterclockwise is S, but your hydrogen's on the horizontal, so that's going to switch to an R. So this is RR. And so let's check this one out here. We have 1, 2, 3. 1, 2, 3. So S, but then you have hydrogen there, so S goes to R. And then this one here, you have 1, 2, 3, and that's counter, S goes to R. So this one's RR, and I get that these would be the same. but I wonder if I counted them wrong. So just check that out and see. The book's saying that they're in enantiomers. So just work that out and see if you have something different. You can. Okay, the next problem, we want to convert them to Fischer projections. Excuse me. So you want to put your highest oxidized carbon. This is your carbon chain, 1, 2, 3. You want to put that on top. And your lowest then would be here, CH3. And then your asymmetric carbon would be at the horizontal. And in this case, if you have OH coming at you, you could do this. And then you can always check it by doing 1, sign the R and S, 2, 3, 1, 2, 3. So that's R, and that's clockwise. It would stay R because hydrogen's in back. And then you can check it here, 1, 2, 3, 1, 2, 3. That's counterclockwise, but hydrogen's coming at you. So S would go to R. So that would be correct. Okay, the next one we have CHO, which is aldehyde. This is your asymmetric carbon, so that would be on your horizontal, and your lowest oxidized carbon would be the CH3. Okay, so in this case, let's put bromine on the left, hydrogen here. Actually, let's not do that. Okay. Well, we can just do it. Let's just see. 1, 2, 3. 1, 2, 3. That's R. R goes to S because of hydrogen, so this is S. Let's see what this one is. 1, 2, 3. 1, 2, 3. That is S, but the hydrogen in the back, so R. So then you can just rewrite it and put the bromine on the other side, and this would be your R. Okay, this one you have 2 stereocenters and your most oxidized carbon in the chain. This first one here, so that gets the top. And then you're going to have 2 asymmetric carbons, 1, 2, 1, 2, and then the CH3 is going to be at the bottom. And so if you put the bromine in back, hydrogen over here, and then these are going to be opposite of each other, OH and hydrogen. That's what makes it nice to see when you're making Fischer projections. And go ahead and check this. So this first one here, bromine's 1. This would be 2 and 3. 1, 2, 3. That's clockwise. That's R. But you have your hydrogen coming at you on this carbon, so this would be S. So the first one would be S. And then here we have 1, 2, 3, 1, 2, 3. That is counterclockwise, which is S. So we have S and an S. So let's see what we have here. 1, and this would be 2 and 3. So R, and then R goes to S. So the first one's drawn correctly. And then here we have 1, and then 2, and then 3. 1, 2, 3. That's R, but then hydrogen's coming at you, so that's S. So that's correct. Okay, and the next one, we're going to put this CH2OH on top. We have 2 stereocenters here, 1, 2, so we're going to have 2 crosses here, and then the CH3 will be on bottom. And we see that the OHs are on the same side. So we can just go ahead and draw them on the same side. And I would always check this. So this is a 1, this is a 2, and a 3. I would sign priorities. So that's clockwise. Clockwise is R. The hydrogen's in back, so that's good. The next one is 1, 2, 3. That's R. So we're dealing with RR. Let's see what we have here. 1, 2, 3. That's R. So we obviously, the R will then go to S. So that's not drawn correctly. So let me put the OH here. And then we can do it again here. 1, 2, 3, 1, 2, 3. That's S, and then S goes to R. So it should be over here. And yeah, I guess the way that's written. So this should be your compound. Convert the following Fischer projections to the perspective formulas. All right, so once again, the easiest way to do this for me is just to assign R and S. So 1, 2, 3, 1, 2, 3. That's clockwise, so that's R, and then the hydrogen is on the horizontal, so we'd have to make that as an S. So then when we draw our carbon here with CH3 and COOH, we've got to put something here and something there. And if you put the hydrogen in back and the amine in front, then you assign 1, 2, 3, 1, 2, 3. That's R, but that's not what we want. So then you can just reverse it. And you can put the hydrogen coming at you and the NH2 going back. And then you're finished. Okay, this one here, aldehyde would be number 2. The OH would be number 1. The CH2OH would be number 3. So 1, 2, 3. That's counterclockwise. So that's S, but you have hydrogen coming at you. So S is going to switch to R. So this is R. So when we draw this, we draw a carbon, kind of our backbone. This is the CHO. This is the CH2OH. And then you can just put an OH here and a hydrogen. And then you can just do your priorities. 1, 2, 3. 1, 2, 3 is R. So that's good. Okay. Let's go to the next one. Bromine is going to be 1 with a 79, and then chlorine, and then 3, and then 4. This one doesn't have a hydrogen. Is 4. 1, 2, 3. Ignore your 4. That's counterclockwise. Counterclockwise is S. Hydrogen, or not hydrogen, but the CH3 is your lowest priority, and it's on the dashes, so it's already going back. So S will stay S. So when you draw this, you can just draw your CH2OH up here, your CH3 here. Then you're going to draw something on the dashes and the wedges. So I just would put something in and then see if I have to erase it. So this is 1, 2, 3. 1, 2, 3. Actually, well, 1, 2, 3 is S, but this is your lowest priority, so that would be R. So what you could do is you could just put bromine there. Let's see if this will work. Put CH3 back. So that's 4. Bromine's 1, chlorine's 2. 1, 2, 3. So that's R, and it would stay R, but we want S. So let's do this again. CH2OH, bromine. Let's do the CH3 and the chlorine going back. Now you got 1, 2, 3. That is R, but the methyl is coming at you, so that would be switched, so that would be S. All right, so that would be your compound right there. Okay, we have 2 stereocenters here, so we're going to have to do this twice. Bromine's 1, this would be 2, and that would be 3. 1, 2, 3 is clockwise, R, but your hydrogen is on the horizontal, so the first stereocenter is S. So this one's S. Okay, the next one, 1, 2, 3. 1, 2, 3, that's counter, which is S, but your hydrogen is on the horizontal, so S goes to R. So the next stereocenter is R. So when you draw this, you could just draw it like CH2OH, CH3. You're going to have your dashes and your wedges, and then you could put hydrogen on the same side here, bromine, and that should actually be chlorine. Chlorine's with the bromine, and so let's just check it. So you got 1, 2, 3, 1, 2, 3. That's counterclockwise, so that's S, and that's correct. And then the other one here is chlorine 1, 2, 3, 1, 2, 3. That's clockwise, that's R, so that's good. Okay, this is your last assignment, 5.3, and we're looking at the relationships between compounds, whether they're enantiomers or diastereomers. This problem here, dibromohexane and dibromohexane, and the bromo is connected on the 2,3. The 2,3. So the only thing that's different is this 2R, 3S, and 2S, 3R. Let me just go ahead and tell you, the R and the S are opposite, the S and the R are opposite. So RS and SR. This means they are enantiomers. What we're dealing with here is when we have more than one stereocenter. So if you had something like RS and SS, these would be diastereomers. So in order to have an enantiomer, R has to be exactly the opposite, which is S, and S the exact opposite with R to be enantiomers. Okay, so looking at this one, we have dibromohexane, dibromohexane. The dibromo is on the 2 and the 3. So what do we have? We have an R and an S, and we have an R and an R. So these are going to be called diastereomers. And remember, diastereomers, they can be separated by recrystallization. Boiling points are different, so they have different physical properties, but enantiomers cannot. They essentially have the same properties, except that they rotate light differently. Okay, so see, the best way to do these, I think, is to assign R and S. Are these the same compound? 1, 2, 3, 4. 1, 2, 3, 4. So this is 2, 3 dibromobutane. When you name them that way, you know whether they're the same. So this is obviously 2, 3 dibromobutane. So the question is, are these the same? Well, let's look. So this is a 1 priority. This would be 2, and this would be 3. So 1, 2, 3 is counterclockwise, which would be S, and the hydrogen's in back. So that would be 2S. And then the next one, which would be this compound here, or this carbon, 1, 2, 3. So 1, 2, 3 would be counterclockwise S, but the hydrogen is coming at you. So the S would go to R. So this would be 3R. Okay, keeping with the same logic here. 1, 2, 1, 2, 3, 1, 2, 3, counterclockwise. So that's S, but the hydrogen's coming at you. So that would be R. So that would be 2R. And then you go to the next one, and the bromine's 1. This is 2, 3, 1, 2, 3. That is clockwise, which is R. And so that's 3R. So these would be diastereomers because they're not exactly opposite. So this is a diastereomer. Remember, Cysts and Trans are diastereomers. Okay, looking at this one here, you have 1, 2, 3. So the name of that would be actually 3-bromo cyclohexane, ENE. This one would be 1, 2, 3, 4, 5, 6. This one would be 4-bromo cyclohexane. So these are different compounds. What do we call those? Those would be structural isomers, constitutional isomers. Structural, they have a position of the alkene in a different place. Okay, this compound here, remember when you see these bicyclo compounds, the best way to solve them is to draw the mirror image. And so if you were to draw the mirror image, then you would rotate it 180 degrees. So what is in back must come in front, and what is on the left side must come to the right side, and then you can compare the number 1 structure and number 2, and you're going to set it on, try to superimpose it, and you see that this chlorine's in back and this chlorine's in front. So these are chiral. These are enantiomers. And so, oh, I drew it wrong, didn't I? So let's put the, instead of putting the chlorine there, put the chlorine there, so we don't have to redraw it, and then just put the chlorine there. And once again, they're still enantiomers. So those are enantiomers. Okay, this compound here, this would be let's see, I guess in diastereomers, but let's just do the assignment. 1 CHO, so that's carbon. That carbon is bonded to 2 oxygens because it's a carbonyl. And that carbon's only bonded to 1, so that's going to be 2, and this will be 3. 1, 2, 3 is counterclockwise. Counterclockwise is S, but then your hydrogen is on the horizontal. So the first one is R. Let's look what we have here. Okay, so here we have 1, 2, 3. That's R, and that goes to S. Okay, so this one's S, and this one's R. So it depends on this one here. And let's go ahead and assign it 1, 2, 3. 1, 2, 3. Counterclockwise is S, but your hydrogen's on the horizontal, so that's R. So this one's RR, and this one would be 1, 2, 3, and that would be counterclockwise S, which would go to R. So this one would be SR, and this one's RR. Because it's not exactly SS and RR, this would make these diastereomers. Okay, and looking at the last one, let's see, we have, look, these are mirror images of each other, okay? So since these are mirror images of each other, they are going to be enantiomers. You see the OHs are on the opposite side here. The mirror images, so if you were to rotate this one, so what's on bottom here, when you're doing Fischer projections, what's on bottom becomes on top. So this is on top, and now that will be on bottom. And what is on the left side becomes the right side, but this is on bottom, so you're going to have to go H, OH, OH, and then this will be on top now. So this is H, H, OH, and then you compare these two structures and you see that they are not superimposable. So they're chiral. Those are mirror images, so that's an enantiomer. Okay, which of the following pairs of compounds can be separated by recrystallization? So what you need to know here is that diastereomers can be separated by physical processes, recrystallization and distillation. Okay, enantiomers cannot. So basically what you're asking yourself is to figure out what's the relationship here. A meso compound with a plus minus would be diastereomers. And so therefore they would be separable. So yes, these would be separable. Here you have 2 asymmetric carbons. You have an asymmetric carbon here and here, here and here. Since these are diastereomers, they can be separated. So yes. This one here, you still have two stereocenters, but if you do your R and S here, you'll see that this is 1, 2, 3, 1, 2, 3. So what is that? Counterclockwise. Counterclockwise is S. Bromines in back, so this is R. So this first one is R. And then here we have 1, 2, 3. 1, 2, 3 is clockwise, which is R, and it stays R. So then let's see the relationship here. 1, 2, 3. 1, 2, 3. That's counterclockwise, that's S, and the hydrogen in the back, so that's S, that's okay. And then let's look at this one, 1, 2, 3, that's R, but the bromine is going in back, so that's going to be S. So you see that this is RR and this is SS. That means that they're enantiomers, and enantiomers cannot be separated by physical means, so no. Okay, so on this one, each structure you want to label the asymmetric carbons and then label them RS. Decide whether they are chiral or if they are meso. So if you do the first one, you'll see that it is R and that is chiral. So the assignment is 1, 2, 3. 1, 2, 3 is counterclockwise, but you do not have your hydrogen in back, so that would be R. This is your asymmetric carbon here. This is a Fischer projection. And so when you sign 1, 2, 3, 1, 2, 3, you see that's counterclockwise, which is S, but your hydrogen's on the horizontal. So this would also be R, and that would be chiral, because you have a asymmetric carbon. This next one, if you do the assignments, this carbon, oh, sorry, not that carbon. This carbon would be S, and this carbon would be S, and therefore this would be chiral. This carbon here would be S, and this would be chiral. This here has a plane of symmetry, and because everything on this side is the same as everything on this side, this would be a meso compound and it would be a chiral. This one, however, this top carbon would be S, and this bottom carbon would be S, so it would be chiral. Here, this top carbon would be S, the bottom carbon would be R. This one is also chiral. This compound here, I will have to do the assignment. 1, 2, 3. 1, 2, 3 is clockwise, which is R, and then we go to S. So this carbon is S. We have 1, 2, 3, 1, 2, 3 clockwise, which is R, and that would be S. So this would also be S. And then this carbon here would be 1, 2, 3. That would be counterclockwise, which is S, and then we go to R. So that would be R, and it would be chiral. This compound here, you need to draw, when you have these restricted Alanine type carbons, you need, or Alanine structures, you need to draw the mirror image. It's kind of like those bicyclo rings. So we've drawn the mirror image, and now, okay, here's your bromine. What's in back for your mirror image, when you rotate it 180, comes in front. So I'm going to just draw this here. The bromines now are in front, and the chlorines are in back. Now this is our first compound, and this is our second compound, and we're going to compare these two. And if you try to lay number 2 on number 1, you'll see that the chlorine here are in back and the chlorine here are in front. So these are chiral compounds right here. This is chiral. Okay, this compound here is a chiral molecule, and if you do your assignment, you'll see that that's an S. This compound has a plane of symmetry. This is achiral. If you couldn't see that, you could just try to see if you had an asymmetric carbon. So you have bromine, which is different. You have hydrogen, which is different. But then when you go CH2, CH2, you see that you come to the same place, and there's no point of differentiality. This compound here is one of the bicyclo compounds, so you need to draw your mirror image. You need to rotate it. And so in this case, what is on the left-hand side will be on the right-hand side. As you can see that this is achiral, because you can superimpose those. Same thing here. So let's draw this real quick. And then you rotate it, the mirror image. Now, back here, the carbonyl is going in the back. Now the carbonyl will be in the front. So when you compare these two structures, you can see that this carbonyl is in back and this one's in front. So those are enantiomers. So this is a chiral compound. This compound here okay, so our next compound is this compound here. And if you do your assignment, you'd see that this is chiral. So where's your asymmetric carbons? There would be your asymmetric carbon, and it should be an R. This is actually a good one for you to work on assignment. So that would be 1, 2, 3, and you can see that that would be R. Okay, menthol here, where are your asymmetric carbons? There's one, there's one. So you have 3 asymmetric carbons. So see if you can do this one. The first one, R, this one should be S, and this one should be S. Okay, the next compound here are Newman projections, and in your Newman projection, I think it'd be best for you to just convert these out of Newman projections. So here you have CH3, you have a carbon with a fluorine. You can make that coming towards you. And then you have this ring, which is a carbon, and then it's bonded to a CH3. And then if fluorine's coming at you, and you have nitrogen coming at you, NH2, then what's going back is the hydrogen here and the bromine. So hydrogen here and the bromine is coming back. I will not make you have to assign these for your exams from the Newman projections. I just want you to be able to convert them. But I basically have 1R, 2R. Okay, it's kind of important to be able to draw these names to structures. So to draw 2-chlorobutane, you need 4 carbons, and then you need chlorine coming on the second one. 1, 2, 3, 4. So if this is 1, 2, 3, and that would be R, then you would want the chlorine going back and the hydrogen coming forward. And that way you can switch it and it would be S. So you need to have your dashes and your wedges on the same side. Okay, the next compound here is cyclohexane, and then 1,1-trimethyl. So that's 1,1, and then 2 is another methyl. Now, your asymmetric carbon would only be this one here, and it's saying it needs to be R. So if you make this go back, and you make your hydrogen come at you, let's see. And then just try it. Okay, if it's not, then we make it the other way around. So this would be carbon number 1, carbon number 2, carbon number 3. 1, 2, 3, that's counterclockwise. So that would be S, and then S would have to go to R because hydrogen's coming at you. So that would be correct. Okay, the next compound, dibromohexane. And so let's draw this 1, 2, 3, 4, 5, 6, dibromohexane. And then on 2 and 3, we have to put the bromines. Okay, and then 2, we need to have an R. So let's just see, and we'll just put both of those on there, and then if we have to switch them, we will. 1, 2, 3. 1, 2, 3 is clockwise. So this is R, and that's good. There's 2R. Okay, here, 1, 2, 3. That is R, and we don't want R. So then we're going to redraw this, and we're going to put bromine coming at you here, but then on this one, we're going to make bromine going back, and that should be correct. The next one is dibromocyclohexane. So if we do this, put bromine coming at you and bromo going back. Let's see what we have. 1, 2, 3. 1, 2, 3 is R. And so that's 1R. Okay. And then here we have 1, 2, 3. That would be S, but then S has to go to R because you got bromine, which is a high priority going back. So this would be correct. Mesohexane diol. Let's do this using a Fischer projection. CH2, CH3, CH2, CH3. So that's 1, 2, 3, 4, 5, 6. And you want meso, so you want a plane of symmetry. So basically you're going to want the OHs on the same side. So that would be the best way to do meso 3, 4, 1, 2, 3, 4 hexane diol. Same token, if you want to, that's one problem. If you want to do the enantiomers, you would just, let's do the Fischer projection because it's easy. So you'd have OH on one side, OH on the other, and then you would make its mirror image. So OH would have to be on the other side, OH and H. Now, you couldn't tell which one's plus or which one's minus. This is a racemic mixture. So that means 50% would be one enantiomer and 50% would be the other enantiomer. But only by doing the experiment of rotating plain polarized light could you determine which is plus or minus. It still doesn't determine which one is actually R or S. It has to be experimentally determined. Okay, the last one, I think this is the last one, yes. Okay, give the stereochemical relationships between each pair. They can either be the same compound structural. You guys, I've noticed that I made a mistake here, so let's go ahead and fix this. This should be, in this one, this should be a hydrogen here and a hydrogen here. Okay, so let's do this. These compounds here are the same compound. This would be meso because they have a plane of symmetry. So even when you draw the mirror image, these are the same, okay, because there's a plane of symmetry. So that's a meso compound, and those would be the same. This one here, you see that this is different than this. So these are different, and these would be the mirror images, and these therefore would be enantiomers, because you could rotate this 180 degrees, and then what is on top will go on bottom. So CH2OH goes on bottom, the methyl goes here, and then what is on the left hand side is going to go to the right hand side when you rotate this. And then if you compare compound number 1 with compound number 2 and you try to superimpose it, you see that they're not superimposable simply because this is on bottom now, CH2OH, and over here it is on top. This makes them enantiomers. Okay, this one here, these methyls are the same. And so this is a mirror image. Okay, so this is a mirror image. So when you rotate this, what's on top goes on bottom. Now this will go OH over here, and this one here will be an OH on this side. And then when you superimpose these, you see that they are different. So these are enantiomers. So the mirror image is an enantiomer. Okay, this one here, when I get them drawn like this, I just go ahead and do the R and the S. I make sure the connectivity is the same. So let's name it. There's 2 carbons here. So this is going to be 1 bromo, 1 chloro, ethane. And this compound is the same. 1 bromo, 1 chloroethane. Okay, so then let's just assign priorities. 1 for bromine, 2 for chlorine, and 3. 1, 2, 3 is clockwise, which is R, but the chlorine's in back, so the first compound is S. Let's do the next one. 1, 2, 3. Connect the 1, 2, 3. That's clockwise, which is an R. The hydrogen is not in back, so then we switch that to S. This is S. These are the same. Okay, they are the same. They're both S. Okay, this one here. This is Cysts, and this is Trans. You can sign the R and S. You will find that these are diastereomers. This one, these are a little bit harder, and like I said, I'm not going to ask you to do these, but I do want you to be able to convert just what the name is. So CH3, this is a carbon. I want you to be able to see that that's OH and an H, and then this goes to this carbon here, which is the blue. Call that the blue, and the blue is connected to a CH3, connected to a bromine, and it's connected to a hydrogen. Now the key is these are in the same plane here. So this would be the same plane. CH3, this carbon, and then technically this would be hydrogen like that. So that would be the plane. And then this is, so if that's the plane, this would be on the same side. So you would make OH facing towards you and CH3 facing towards you, but you'd have to actually draw it like this, where CH3 is on, and the OH on top, and then you would draw the hydrogen and the bromine going back. So if you wanted to really convert those, that's what you'd have to do. And then you could do the same thing here. If you want your plane here to be, this is your plane, you would do hydrogen, carbon, that would be your red carbon. This could be your blue carbon here, and then your bromine here, and then you would make your OH on the same side here. So this would be coming at you, OH, this hydrogen's coming at you, and then these methyls would be going back. And then what you could do is then you could assign your priorities. So this would be 1, 2, 3, 1, 2, 3 clockwise, which is R, and you have the hydrogen there, so that's R. This one here, you have 1, 2, 3. 1, 2, 3 is counterclockwise, which is S, but your hydrogen is not going back, so this is R. So the first compound is an RR, and then this compound here, 1, 2, 3, that's clockwise, which is R, but your methyl is not going back, so this would be S. And then you do the same thing here, 1, 2, 3, 1, 2, 3, that's clockwise, which is R, but once again your hydrogen is not going back, so this would be S. So this one's SS, and this one's RR. So this would mean that these are enantiomers.